Welcome. My name is Orland Whitney. I'm the team captain for Team NMSU. I'll be presenting our design for the Ball State University use case. We titled our project OASIS, which stands for Optimized Architecture for Sustainable Innovative Spaces. Most of you know that some of our team members will turn off their video feed to improve bandwidth and to be able to better answer your questions. Our team is composed of a diverse and skilled group of students at different stages of their education, from graduate students all the way to a high school dual credit student. Our approach is to design cost-effective and efficient PV systems and battery storage for our university customer, which offers savings, resiliency, and the versatility to utilize an electric vehicle fleet for its students. We also designed a building integrated photovoltaic or BIPV system for the architecture building glass curtain wall and included a solar hot water solution for the building as well. We validated our design's respective impacts on the distribution system using Open-DSS. And finally, we performed financial analysis to calculate net present value of 0 over a 20-year period and offer battery stack benefits. As with any good PV design practices, it is important to know locational latitude and longitude to properly position PV modules. The images to the right show the areas that were presented to us, both the campus and off-campus plot of land. We have designed 9 building rooftop arrays, a parking structure array, and a ground-mounted PV array. The buildings which are to receive PV systems are Neuer Complex, Bracken Library, Emmons Structure to the left, and the Telecommunications Department on the right. Emmons Parking Structure, Robert Bell at the top, Whitinger Business Building to the right, the Art and Journalism Building, the David Letterman Building, and finally, the Center for Architecture and Planning. Additionally, we integrated attractive PV benches for the throughway BSU calls the cow path. Finally, the off-campus design combines a 2.8 megawatt rated ground-mounted PV system with a 3 megawatt utility storage system. This is located near the Facilities Planning and Management Building, which also presents the best serviceable location since all of the O&M personnel offices are there. Utilizing a utility-scale SMA inverter, ground-mounted PV systems will be grid-tied. Additionally, solar energy may be integrated into the campus bus transit system with a vision for electric buses and charging stations near the large ground-mounted PV area. This table shows the total of all PV systems we have designed for the campus. As you've seen on the previous slide and from details in our report, our rooftop designs have a diversity of tilt angles and array orientations ranging from east, southeast, and south to southwest and west. These are the subsections shown for multiple subsected rows. These variations in the design result in a beneficially high diversity throughout the day because we design PV systems to vary in azimuth orientation. This results in flattening of the duct curve. Additionally, this reduces temporal coincidence of PV generation profiles, thus reduces coincident voltage and line overloads. All of our PV systems were designed as 3-phase systems, with the exception of smaller BIPV systems on the architecture building, which is single-phase. Our largest rooftop array is 345.6 kW at the Telecommunications Department. The parking structure we propose PV for is 1.1 megawatts. The ground-mounted PV we've designed is 2.8 megawatts. Total kW for the campus design is 5.2 megawatts DC. We utilized just 2 companies for our systems, Canadian Solar for modules and SMA for inverters. We did this because both offer excellent benefits for the cost of components, and both companies have long track records for reliability and efficiency. As traditional PV system design dictates, we started by laying out PV arrays facing due south and at an optimal tilt angle for any location in the Northern Hemisphere. We have submitted these designs as progress deliverables in November. Upon close examination, it is apparent that most of the layouts do not utilize available rooftops sufficiently. This is due to the inherent roof geometries, building orientation, too many obstructions on the roof, or all 3 of these factors taken together. We also wanted to utilize the best practices of installation time-efficient PV systems and racking solutions, and we concluded an east-west aero-compact racking system would provide higher yearly energy yield. To verify this hypothesis, we compared yearly energy production for south-facing and east-west facing arrays, while also varying row-to-row spacing to avoid row-to-row shading. The table above shows results for this comparison, showing that all the east-west aero-compact system indeed results in higher yearly energy yield. Again, this is due to the fact that we could install greater energy density in this configuration for a given building without violating NEC and international fire codes. We defined all required setbacks and clearances in Aurora to be 6 feet from the building perimeter and provide 4 feet of clear access to all roof penetrations, including roof drains. This enables fire personnel to vent hot and toxic air with their axes in the event of a fire. The figure on the left shows the same rooftop array with stringing configuration for the inverter. A different approach was utilized for the parking structure. Here we employed a safety-centric design. It is critical that no snow nor ice melt fall on vehicles or pedestrians during the winter months because of the resultant damage or injury. We therefore chose a concave design which directs snow and ice melt to dividing walls within the parking structure and out of the common traffic areas. This is one of the largest systems we proposed and creates a positive PR for BSU. Throughout this challenge, it has been our goal to utilize every software to its fullest. We began with the goal of learning Aurora's design software, but that goal soon changed to striving to push the limits of the software as we learn more. From the center and going clockwise, this is a quick confirmation of the manual stringing at Emmons Auditorium, a dual tilt array where we directed all wires to separate inverters based on orientation. This was done for all buildings with dual tilt designs. Next, at the top left, we have an image of the manual stringing we accomplished at Bracken Library to 1 central inverter. Next is the rooftop at the Telecommunications Department. I think this image really illustrates well how Aurora can make you feel you're actually standing on a reimagined rooftop. Continuing in the bottom right-hand corner, this is where we utilized Aurora's rooftop software to lay out a ground mount array. Believe it or not, this is one continuous rooftop. This really allowed us to add or subtract panels without deleting dozens of rows of panels, as clearly many new solar design softwares are not optimized for this task. That said, Aurora really helped us utilize this vision. Left of that, we have the Whitinger Business Building, an illustration of how this design software allowed us to accurately model rooftops, trees, and obstructions to LiDAR. We laid out walkways, defined obstructions, and told our panels where to go. The architecture building at BSU has been designed to utilize a variety of passive solar and thermal solutions, as shown in the upper right. Our team challenge was to design a BIPV retrofit solution to replace the existing glass curtain wall, as well as suggest a retrofit solution for the entire hot water system. We have selected Onyx amorphous PV glass for the BIPV solution. We have carefully selected the best Onyx PV solution to be dimensioned per BSU architectural drawings over the existing mullions and trusses. We also created an Onyx PV model by following the Onyx MSDS and Aurora Solar to get an accurate PV production model. As you can see, we were able to get a 100% coverage with dimensioned Onyx glass BIPV solution over the existing glass curtain facade. We have selected Apertis evacuated solar hot water heating tubes as a retrofit to the current water heating solution existing in the upper right-hand corner of the building. A large 2,800-ton tank will service the building and will likely be situated at ground level to do so. A Well-McLean electric hot water booster would help with maintaining water temperature during the late operating hours and cloudy days. And a Takeo 250-volt AC high-capacity hot water pump will provide the superior water pressure throughout the building. At first, and for our interim deliverable, we submitted a design which had a single-axis tracking PV system laid out on this plot of land. But as we went through our use case, we could not help but notice that the land outline resembles the BSU mascot, the cardinal. So we drew the inspiration from other successfully completed projects, such as a 15-megawatt PV system shaped as a panda in Dakong, China, and a Mickey Mouse PV system at Disney World in Orlando, Florida, currently operated by Duke Energy. Thus, we designed a cardinal-shaped and BSU logo-shaped PV system for the off-campus ground mount PV system. As actual PV system costs continue to decrease, the PR value improves, and we think a Google Earth image or flyovers for tourists and alumni will serve as an immense amount of PR value payback. Therefore, we designed a PV array made out of 11,016 flat-mounted Canadian solar PV panels with an additional backfill of colored gravel to produce the desired effect of BSU's cardinal and logo. Again, this is a ground-mounted PV system. Total rating is 2.8 megawatts. We carefully scaled and planned this installation to consider the maximum benefit for Ball State University, including the number of trees that would need to be removed, land that needs to be graded and secured with fencing, and the soil hardness for the proposed pile driving. We factored in the cost of driving helical piles at the edges of the array with standard piles at the center. Furthermore, we decided that because colored solar is fairly new technology without reliable track records, we opted to illustrate the color of the cardinal using colored gravel rather than colored panels. Red has a tendency to become sun-washed over the years of sun exposure, so it could likely turn a salmon or pinkish color. We did not want to risk that likelihood in our design, so this has the added benefit of preventing overgrowth and resultant unnecessary shading of the panels. As part of this challenge, we needed to perform distribution system modeling. This is typically done with a software called Open-DSS. First, the Open-DSS campus model was validated. It is shown on the right as blue lines representing the distribution system. We then analyzed yearly campus loads given to us by BSU, shown in the graph on the right. We realized that the campus load provided in the use case showed extreme load drop-offs to less than 5% of total load, even during business hours. While this may not be a realistic situation in real life, this is exactly when PV power will be exported. Since no power export was one of the primary conditions for our use case, our next challenge was to size and rate the battery system, which would mitigate this. The big question we need to answer is, can BSU's distribution system accommodate the PV systems and storage system we are proposing? Hosting capacity is defined as the maximum amount of PV that a feeder can accommodate before adverse impacts occur. This value will be dependent on the feeder, PV deployments, monitoring criteria, and load. The flowchart on the right shows a progression for performing the hosting analysis. These steps are as follows. Add 5 kW to all buildings which were targeted for PV installations, run a yearly power flow solution, check for overloads and any voltage violations on all buses within the system. If no violations are detected, add 5 kW increment to all buildings again and repeat. Repeat steps 1 through 3 for typical meteorological data, yearly weather conditions, as well as for the best day, clear PV irradiation pattern, and an overcast day, which is only 10% of TMY daily PV irradiance. We used our own PV shapes, which we have exported from Aurora hourly energy production using our PV design. We also synthesized clear, overcast, and cloudy day PV load shapes for the hosting analysis steps described next. Figures on the lower left or on the lower right show the voltage distance profile plots for without PV systems and with all PV systems for the entire distribution system. We can see that all primary voltages are within the allowed ANSI ranges, which are shown as red lines. The figure on the upper right shows both maximum and minimum voltages anywhere in the feeder for cumulative PV size up to 4 megawatts. Again, we do not see any violations. The first figure shows results of a yearly simulation of campus power flow before any PV addition. Real power is shown in black and reactive power is shown in red. This next figure shows a yearly simulation of campus power flow after we have added our PV systems. Negative excursions, or real power, shown in black, indicate power which will be exported by the campus distribution system onto the Indiana power system. Since our use case requirement stated that no power export was allowed, we needed to size the battery storage system to absorb all the PV power generated above the campus load on any given day and hour. This next figure shows the yearly power flow solution after we have sized and added the battery PV system. As you can see, all negative power export has been remedied. The figure on the bottom left shows the same information, net campus load before PV with all PV systems added and after battery system addition, but is expanded to see better details. These results show that in order to achieve zero power export, BSU's use case required a minimum of 3 megawatt, 7 megawatt hour storage. To meet the requirements for the previous slides, we're proposing 3 1 megawatt LG utility battery energy storage systems. LG provides a turnkey solution for a highly efficient 1 megawatt, 2 megawatt hour PCS of 98.7%, which is shipped in as a shipping container with its own power conditioning system, or PCS. This system is also capable of operating in an islanded or grid forming mode, which could be a very valuable feature should BSU campus decide to operate it as a microgrid. We have verified that LG Chem PCS is indeed capable of all the controls functions we've specified for stacking of benefits. Indeed, LG Chem PCS is capable of even more advanced fast response functions, such as operating in voltage source or current source mode, variable power factor operation, volt var, and volt watt support, which are beyond the scope of this project. Our 2.2 megawatt SMA Sunny Central utility scale inverter, which we've selected for the ground mounted PV system, also has an additional capability with battery systems, compatibility with battery systems. It has an additional DC input to allow PV plus storage systems to be DC coupled. This is a valuable feature as it can increase overall system efficiency by eliminating two DC AC and AC DC conversions. Further, we envision that an EV, including bus charging infrastructure, co-located with the 2.2 megawatt ground mounted PV system and BESS will provide load offtakes as well as defer upgrades to substation infrastructure. A multi-vehicle charging station, such as an ABB Terra shown here, could be a beneficial feature for electrification of the campus. We think that a centralized location of PV plus storage plus EV charging infrastructure is a perfect match to be located near the campus facilities building. Reopt is an open source NREL simulation tool which enables customers and project managers to perform several scenario analyses to find an optimal mix of PV, wind, and battery storage options for maximizing return on investment. We used Reopt to perform simulations for optimization for several cases, finance and resiliency. The first case, shown in figure 2 on the left, shows optimization for finance only. Optimization for finances resulted in the 5 to 7 megawatt recommended PV system size and a small recommended battery size. More on these details are in our report. More importantly, however, we quickly realized through utilization of Reopt the limitations within it, limiting the usability and applicability to our results. The limitations of Reopt were, our BSU case requires no power export. However, Reopt does not have an option for setting zero export of PV power, limiting net metering to 0. As a result, Reopt continued to recommend direct power exports as seen in the yellow filled areas on these graphs. The second limitation of Reopt was not being able to model a complex PV array. Reopt can simulate only a single PV array at one tilt angle and one azimuth angle. Since our proposed PV design included a variety of PV system azimuth and tilt angles, as well as an east-west facing array, there was no accurate way to model our design within Reopt. We have contacted Reopt experts at NREL, and they've confirmed that there is indeed no functionality in Reopt to model complex PV arrays. We could approximate a simple and uniform PV array, which would produce the same energy yield as ours. However, this would result in a difference of daily PV production shapes. Our arrays would produce more power during mornings and afternoons compared to a simple south-facing array. Also, this is why our nominal campus-wide PV system size is 5.8 megawatts, but we're using a value of 3 megawatts for Reopt optimization because we had to rate the system size based on our specific PV systems orientation and tilt angles. The third limitation of Reopt was that the recommended battery usage was less than efficient, as you can see by the fact that dashed lines keep the battery's state of charge close to 100% with only a few discharges. It would be more optimal to keep the battery's state of charge within the range of 75 to 80%. This allows the battery to absorb PV overgeneration when a load of the university is low and charged directly from the PV, avoiding any exporting onto the grid. Choosing anything other than 100% SOC is not currently an available function in Reopt. The only way for us to force Reopt into efficient battery utilization was to perform optimization for resiliency, which is shown in the figures to the right in figure 3 for a 1-hour outage, 3 and 5-hour outages, which recommends an extreme 33 megawatt hour battery capacity for a 5-hour outage. All optimizations involving resiliency were seen to be making more efficient use of the battery. This can be seen by looking at the SOC values and the number of cycles of the battery per the same time period in the plot. This is understandable since, due to the resiliency requirement, recommended battery sizes were significantly higher. Unfortunately, this comes at the expense of having a much higher battery cost. Overall, Reopt is a very powerful optimization tool, but often falls outside the bounds of our use case requirements and our complex organization of PV arrays. Therefore, we have created our own model Excel spreadsheet for optimization of the battery operation, charging and discharging schedule, as well as calculation of customer savings. This spreadsheet and model were included in our report and deliverable. To further optimize PV and battery operation, we need to understand customer utility rates and billing. The utility company which Ball State University uses is Indiana Michigan Power Company under the Industrial Power Sub-Transmission Rate. Details of this rate structure are shown in the table and can also be found in our financial model Excel file, which was included in our deliverable. This tariff is in the form of the block rate system. A block rate is a type of tariff which charges customers a different price depending on how much electricity they've used. The billing determinants for tariff 323 industrial power sub-transmission voltage and its corresponding rate riders displayed on this slide are split into 3 categories. Orange represents the customer service charge applied per meter, blue represents the energy charges applied per kWh, and green represents the demand charges applied per kWh. There's also an energy adjustment formula that rewards BSU for having an average monthly power factor of over 0.85 and penalizes BSU for a power factor average of less than 0.85. Depending on the monthly average power factor, the constant from the energy adjustment formula either reduces or increases the amount of billed kWh.
And I'll just go ahead and stop right now because I think I'm running out of time here.